Okay, so at this point we're going to take a look at a complex voltage divider. This is something that we saw in the lesson, and it's not too difficult to get through. It's just a matter of keeping your thoughts and your notes organized. Ultimately, we'd like to find out what the voltage drops and resistance values for the resistors are. What are these resistors called?
Load resistors.
Bleeder resistors. Okay? And when we refer to the bleeder resistor, what resistor are we talking about?
Closest to the reference that is on the side with the most current.
That's correct. Excellent description. So let's take a look at that. Which side has the most current? Top side, okay? What do we call that when the point above or below the reference has more current? What do we call that current? The total load current, correct. So the total load current, ITL, right? And what is that value for this circuit, ITL? 305 milliamps. 305 milliamps. Okay, now that we have the total load current, what could we find?
Bleeder current.
The bleeder current. How do we find the bleeder current? We take ITL, multiply it times 11%. And that gives us 33.55 milliamps. Now what do we do with that bleeder current?
Add it to the load current.
Add it to the total load current, and that gives us our
Line.
current or our total current, IL or IT. And what is that value? 338.55 milliamps. Sound good? Okay. What do we know about that total load current? What do we know about it? Where does it come? Where does it go? It goes back to the source. And if it goes back to the source, then where must it come from? The source. So we would have 338.55 milliamps of current going that way, yes? Now, at this node right here, what happens to that 338.55 milliamps? It splits. In what way?
Going down to load 5.
How much goes to load 5? 180 milliamps goes to load 5. And how much continues across R5 then?
158.55.
158.55 milliamps, because current is additive at the node. Therefore, of this 338.55 milliamps, 180 milliamps goes to load 5, the rest goes across R5. What happens to that 158.55 milliamps at this node? It splits, right? 100 of it goes here to load 4. What happens to the rest? It goes across R4. That's 58.55 milliamps. Now, we didn't do a redraw here, but what do we know about all of these loads and the reference? They're all in parallel, or they share a common point. The common point is reference. So I'm going to go ahead, I'm going to erase the references here, and I'm going to connect them all so we all know what we're talking about. And I'll draw the one reference right there. Okay, any questions about that redraw? Okay. The next thing we'll do is we'll take a look at these loads and their currents. So what happened to that 180 milliamps that went to load 5? What happened to it? It goes back down, right, into the reference. So I got that 180 going that way. And what happened to that at this node right here? Well, that 100 milliamps went down there too, did it not? So now going out of that node, how much do we have? 280 milliamps. Okay, back up here to 58.55 milliamps. It hits this node, what happens? All of it? What happens to some of it?
It goes across the leader.
And what do we call that? That's our leader current, right? That's your I sub B. We already know what I sub B is. That's the 33.55 milliamps across R3. So the remainder of it goes down this way, right? Which, how much is that? 25 milliamps. Now, at this node right here, we had 280 milliamps coming in, 25 milliamps coming in. How much goes out? 305 milliamps. Now, you can confirm this by looking at your total load current. How much was your total load current? 305. They should match, right? Because this is the current that's going to feed those.